Hello everyone. Today we will study further about the Maxwell's thermodynamical relation. In our last lecture, we have derived Maxwell's thermodynamical relations. These all are actually six total, but out of that, four are considered as the fundamental Maxwell's thermodynamic relation. The other two were based on the combination of mechanical and thermal variables. Okay, that means PV and ST were together separately. Anyway, today's lecture will focus on the application part of Maxwell's law, Maxwell's thermodynamic relation. Particularly, we will see the applications about specific heat equation, Clausius Claypeyron equation. Okay, the objective, as you can understand from the title, the objective of today's lecture to understand the relationship between thermodynamic potential and their variable, and then we will understand applications of the Maxwell's thermodynamic relation. Okay, so the outcome after attending this lecture, you will be able to learn the relationship between the thermodynamic potentials and their variables. The variables are P, V, S, and T, and the potentials are also four. We have defined that they internal energy, then Helmholtz energy, and then enthalpy, and finally the fourth one is Gibbs free energy function. Okay, so we will derive the relationship between the potentials and their variables. And the next outcome will be about the Maxwell relations application. You will learn how to apply these Maxwell relations for various applications. Okay, so here is the content to achieve the objective of today's lecture. The first topic is relation of thermodynamic potential with their variables. It is divided into according to the thermodynamic potential. First one is internal energy, then Helmholtz energy function, enthalpy, and Gibbs free energy function. Okay. And the second topic is applications of Maxwell's thermodynamic relations. Today, in today's lecture, we will consider about a specific heat equation and Clausius Clapeyron equation, the first latent heat equation. We will see some other application in our other lectures. So here is the list of the reference books which you can consider for further study, for the details, and to understand if you are not clear about anything from this lecture, you can definitely contact to me by email or by commenting in this video below in the YouTube channel. Okay, so let us start. The first topic, relation of thermodynamical potential with their variables. You know already that the quantities internal energy, the SB, the function of S and B, the Helmholtz energy F, function of T and B, enthalpy, function of entropy and pressure, and the Gibbs free function, Gibbs free energy function, that is function of P and T, that are called thermodynamic potentials. On the other hand, the thermodynamic variables, entropy, temperature, pressure, and volume, these can be derived from the thermodynamic potential by their differentiation simply with respect to the independent variables associated with them. Okay, so we will consider deriving one by one from each of them. So the first one is thermodynamic potential U, internal energy, that has the variables entropy and volume associated with this. Let us consider to derive this, let us consider the first and second law of thermodynamics, and if we combine these two laws, we get the well-known equation. We have used this equation several times in our previous lecture, that is given by du is equal to tds minus tdv. Okay, now if we take partial differentiation of this equation with respect to variable S and B, that is the variables for thermodynamic potential. So if we take the partial differentiation, what will happen? If we take the partial differentiation with respect to entropy, it will become del U upon del S, and the other parameter, that is volume, here will be constant at this time. It will give the value t, because the differentiation of this will be ds will be 1, the remaining part t is constant in that part, minus p into dv, but since v is constant, this term will be 0. Okay, if we take it with respect to variable v, then it will become del u upon del v at constant entropy equals to, this term will be 0 because entropy is constant here, so ds will be 0, the remaining part will be minus p, since if we do differentiation, dv upon dv will be 1. So that will be the values of these two parts. Okay, these are the relations which actually relate internal energy U with the thermodynamic variables as V and T and P. Right, now we know already that du is perfect differential. If it is perfect differential, there will be no effect whether we differentiate internal energy with respect to S first and later by with respect to V, or the opposite way, if we differentiate internal energy with respect to V first and later with respect to S, these values should be equal to each other. So that's what we are doing here now. We are differentiating with respect to V of this expression, and we are differentiating this expression with respect to S. Okay, so it will become del over del V of del U upon del S as constant V, and since now we are using del upon del V at constant entropy, it will be. Okay, on the other hand, it will become del over del S with respect to entropy of del U upon del V at constant S, and for this differentiation, the volume will be constant. Now, this one we can write, since du is perfect differential, this will be equals, right? If these are equal, what will happen? The term on the other side should also be equal. So here we did what? Del over del v. So it will become del t over del v at constant S equals to, this term will become minus del p upon del S at constant v, and that become our final equation. If you look at this and if you recall our Maxwell's thermodynamic relation, this is the first thermodynamical relation that was proposed by Maxwell. So let us consider it as equation number 2 here. Let us move to the second thermodynamic potential, that is Helmholtz function, or Helmholtz energy function is represented by F, and the variables associated with this are temperature and volume. It is given by the formula we have already seen, F equals to U minus Ts. U is internal energy, T is temperature, S is entropy here. Now if we differentiate this, what we get? dF equals to du minus T into ds minus S into dt, right? It's a simple just a differentiation of this term. Now if we change the value of du from the first and second law of thermodynamics, what we get is dF equals to T ds minus T dv for the value of du minus T ds minus S dt. If you look at this expression, see TDS and TDS both have opposite signs. This is positive and negative, so they will cancel each other. The remaining part will become dF equals to minus PdV minus SDT. Okay, now similar to the first case, we will take the partial differentiation of this Helmholtz free energy with respect to T and V. Okay, now if we take the partial differentiation, so first one is del F upon del T at constant volume equals to, because volume is constant here, this term will be 0, the remaining part will become minus S here. If we differentiate this equation with respect to volume, it will be del F upon del V at constant other variable, that is temperature here, equals to, since temperature is constant, this term will be 0, it will remain as minus P. Okay, this is again equation 3 we can nominate. These are the relations which actually connect the Helmholtz free energy F with thermodynamical variables P, S, V and T. It's very similar as that of first case, right? Now similar to the first thermodynamic potential, dF is also a perfect differential, similar to internal energy. Du is also perfect differential, and similarly df is also perfect differential, so that we will differentiate with respect to the other variable now. So del upon del b of del f upon del t at constant volume, and the total will be at constant temperature. So this should be equal to the differentiation with respect to temperature of this term, because these are the perfect differential. So it does not affect if we differentiate first with respect to v or t. Both should be same. So that's what we have written here. Now if we consider the right hand side of both equations, we will get del s over del v at constant temperature equals to del p over del T at constant volume. And this is our second thermodynamic relation proposed by Maxwell. So we can see we can directly derive Maxwell thermodynamic relation from the thermodynamic potential by simply differentiating the functions. Right. Now let us go to the third potential, that is enthalpy of the system, and the variable associated with this are entropy and pressure. So enthalpy H is given by H equals to U plus PV. If we differentiate it, it will become dH equals to du plus the differentiation of this term will give you PdV plus BdP. Okay, now we can write the expression du as TdS minus PdV from first and second law of thermodynamics. And if you see in this expression, PdV here, PdV here, both are opposite signs, so they will cancel each other, and the remaining part will become dH equals to TdS plus B into dP. Now similar to the first two cases, we will take the partial differentiation of this equation with respect to S and P. These are the variables associated with enthalpy of the system. Right. So if we do the partial differentiation, it will become del H upon del S at constant pressure. That will give you T, because the second term will be 0 at pressure constant. And second one is del H over del P at constant entropy. It will give you V, because this term will become 0 at constant entropy. Right. Now again, similar to internal energy and the Helmholtz energy function, the enthalpy is also a perfect differential, and that's why there will be no effect of the order of differentiation with respect to we are doing. Right. So here we can write del over del P of del H upon del S at constant T at constant for total differentiation at constant entropy equals to del over del S into del of del H over del P at constant entropy, and total is at constant pressure. So these are same, so the right hand side should also be same. If we differentiate this term, del T over del P at constant entropy equals to del V upon del S at constant pressure. That is, that will be equal to each other, and this is nothing else but the third thermodynamical relation proposed by Maxwell. So this is again the third form of thermodynamic relation which can be derived from thermodynamic potential. The last thermodynamic potential is Gibbs function or Gibbs energy function, that has the variables pressure and temperature that are associated with this. So we know the definition, we know the expression for Gibbs function, that is given by G equals to H minus Ts. If we differentiate this, we will get dg equals to dH minus T into ds minus S into dt. Now we can write, because we have already know that dH value we can write from our last section. I mean from here dH we know equals to TdS plus VdP. So we are putting the value TdS plus VdP minus TdS minus SdT. You see here TdS and TdS both have opposite signs, so they will cancel each other. The remaining part will become dg equals to VdP minus SdT. Okay, this is the expression for Gibbs function change with in terms of V, P, S and T. Now similar to the other cases, we will take the partial differentiation with respect to P and T, which are the variables of potential G. So we will do the partial differentiation and get del G over del P at constant temperature equals to B, because this term will become 0 at constant temperature. On the other side, del G upon del T at constant pressure will become minus S, since at constant pressure this term will become 0. Okay, so we get two values. Now again we will consider G is also a perfect differential with similar to the other three potentials. So we will do the differentiation again with respect to other variable, right? So other variable is, for this function it is temperature, for this one it is pressure. So we will do the same thing, del over del T of del G upon del P at constant temperature and at constant pressure, right? That will be equals to del over del P of del G upon del T at constant pressure and at constant temperature. So since the left hand side of both equations are same, the right hand side should also be same, and that will become del V upon del T at constant pressure equals to minus del S upon del P at constant temperature. And this is the fourth Maxwell's thermodynamic relation, right? So we have got four different relations that are Maxwell's relation, and we have also got the values of different variables V as here, for example T and V here. So we can combine, for example, B equals to this also and V equals to this also. So we will combine these into equations, and what we get is, we get these kind of relationship. The thermodynamic variable as T, P and V can be written as S equals to minus del F upon del T at constant volume, that is equals to minus del G upon del T at constant pressure. Okay, this is the first relation. Second is for the temperature, that is given by del U upon del S at constant volume equals to del H upon del S at constant pressure, right? The third relation for the pressure equals to minus del U upon del V at constant entropy equals to minus del F upon del V at constant temperature. Okay, and the last relation is for the volume, that is equals to del H upon del P at constant S equals to del G upon del P at constant temperature. Okay, these equations give the relationship between potential and thermodynamic variables. Okay, now we will see some applications of Maxwell's thermodynamic relation. The first application is related to a specific heat equation. We know already by the definition, the specific heat at constant pressure can be written as Cp equals to del Q upon del T at constant pressure, which will become, because we can put the value of del Q as T delta S, so T del S upon del T at constant pressure, right? This is at specific heat at constant pressure. Now specific heat at constant volume, that can be written as Cv equals to del Q upon del T at constant volume, and that we can write T into del S upon del T at constant volume. Now if we consider that S is a function of T and V, and because we know that ds is a perfect differential, so what will happen, we can write ds equals to del S upon del T at constant volume into dt plus del S upon del V at constant temperature into dV, right? Now if we want, we can differentiate it with respect to temperature, the whole equation. What will happen, it will become, or we can somehow we can divide directly, that is also fine. So del S upon del T at constant pressure equals to del S upon del T at constant volume into del T upon del T at constant pressure plus del S upon del V at constant temperature into del V upon del T at constant pressure, right? Now this term will become 1, so it will be changed to, if we rearrange this equation, it will become T into del S upon del T at constant P equals to T into del S upon del T at constant V into del T upon del V at constant pressure plus T into del S upon del V at constant temperature into del V upon del T at constant pressure So now we have got some equation. Now if we consider Maxwell's second relation, what will happen? The second relation tells us about del S upon del V at constant temperature is equal to del P upon del T at constant volume. So we can write these value, we can put this value here in equation 1. So what will happen? It will become T into del S upon del T at constant pressure minus T into del S upon del T at constant volume. That will become equal to T into del P upon del T at constant P. Okay, so if we compare the values of these two expression, we already considered here Cp and Cv values, they are this one. So we can replace these values in this equation, and the final equation will become Cp minus Cv equals to T into del P upon del T at constant volume into del V upon del T at constant pressure. This equation 1. Now we will, this is the equation for specific heat. Now we will consider some specific keys. Okay, this is the generalized equation. Now we will consider the case for ideal gas. Okay, you know ideal gas equation is given by PV equals to RT, right? Now we can differentiate this equation to get the value of this. So when we differentiate this equation with respect to T, del P upon del T at constant volume equals to R upon V. V we are taking in this side. So R upon V, both are constant when we differentiate with respect to temperature, right? V is constant. So it will become R upon V. And similarly, if we differentiate it with respect to temperature at constant pressure, it will become del V upon del T at constant pressure. So P we can take on that side, and it will become R upon P. So if we put these values in equation 2, equation 2 will become Cp minus Cv equals to T into R upon V into R upon P. So the equation will become R square into T divided by PV, and and Cp minus Cv will become R, because R square T upon RT, so only one R will remain. Cp minus Cv equals to R, and that is the famous Mayer relation for the specific heat at different different constant terms like constant pressure and constant volume. Okay, now this was the case for ideal gas. Now we will consider the case for real gases, and for real gases, gases does not follow the ideal gas equation, they follow the van der Waals equation. So the real gas equation is given by P plus A upon V square into V minus V, that will be equal to RT. Okay, now if we rearrange this, it will become P plus A upon V square equals to RT upon V minus V. Now if we differentiate this with respect to temperature at constant volume, see, we are trying to put the values of these two terms, so that's why we are differentiating this with respect to temperature first at constant volume, and that will become del P upon del T at constant V equals to R upon V minus V, because this term will become 0, and here T will be, the differentiation will be 1, so it will remain R upon V minus V. Now if we differentiate it with respect to temperature at constant pressure, what we get? We will get 0, because the pressure is constant, so this term will become 0, minus V square will come up and it will become V to the power minus 2. When we do differentiation, it will become minus 2 V to the power minus 3. Okay, and similarly we can do the differentiation of the other side also, and it will become 0 minus 2A upon V to the power 3 into del V upon del T at constant pressure equals to, we will do the differentiation of V minus V, so it will become RT upon V minus V to the power 2 or square into del V upon del T at constant pressure. The second term will also come, and that will be to differentiate the temperature with respect to temperature, so it will become 1 and it will become R upon V minus V. Okay, so R upon V minus V, if we rearrange this equation, we will get RT upon V minus V square into del V upon del T at constant pressure minus 2A upon B cube del V upon del T at constant pressure. So this term and this term are common in each expression. It will become RT upon B minus B to the power 2 minus 2A upon B cube into del V upon del T at constant pressure equals to RV upon V minus V. Now, if we take this value to the other side, it will become del V upon del T at constant pressure equals to R upon V minus V divided by this term RT upon V minus V square minus 2A upon B cube. Okay, so we have already get the values for different terms, the first term and the second term. On further solving, we get the final value. So putting these values in equation number 2, what we get is Cp minus Cv equals to T into R upon V minus V into R upon V minus V upon RT upon V minus V square minus 2A upon V cube. Okay, now if we solve this, we will get, we can take RT upon V minus V square outside the bracket, and it will become RT upon V minus V square. In the bracket, it will become 1 minus 2A upon V cube, V minus V square upon RT. Okay, so Cp minus Cv will become T will be cancelled out here, so it will become only R, and V minus V square will be cancelled out with this term. So R equal Cp minus Cv equals to R upon 1 minus 2A upon V cube into V minus V square upon RT. Now, because this term is in square form, right? The value of B is already very small in comparison to volume, right? If it is very small, the square term can be ignored from that equation. So the equation will become Cp minus Cv equals to R upon 1 minus 2A upon V cube into V square upon RT. V is already ignored here. The final expression will become 2A V square. Okay. Now, if we solve this again further, it is V square, it is V cube, it will become only V. So the final form is R upon 1 minus 2A upon VRT bracket. Now, if we take this on the top side, it will become R into 1 minus 2A upon WRT minus 1. Okay. So, if we expand it binomically, we can write 1 minus x to the power something. It will become 1 plus x square plus x cube, so on. So in the same way, we can do the expansion. But since if you see in this expression, the A is very small in compared to B. A is very small in compared to B. If we do the square term, A square will be more smaller than B term. So we can neglect the higher power of this expansion. We can only consider only one term from there. It will become Cp minus Cv equals to R into 1 plus 2A upon VRT. Okay, this is our final relation for specific heat equation of real gas. Right, now we will see the next application of Maxwell thermodynamic relation, and that is known as Clausius Clapeyron equation, and also called it 1 by 1. So you already know if there is a change in the state, either it goes from solid to liquid state or liquid to vapor state, the temperature remains constant if the change take place. At the time of change take place, the temperature remains constant. After that, it can be changed, but at the time of changing, it remains constant. This temperature, either known as melting or boiling, that depends on the different characteristic of each substance, something like or other characteristics, right? So the above, this discussion shows how the melting and boiling point varies with pressure or other characteristic. And this relation, the Clausius-Clapeyron relation, told us about the behavior of melting or boiling point with respect to pressure. And this was achieved by the application of second law of thermodynamics. So somehow we can say that it was using Maxwell's thermodynamic relation, because Maxwell thermodynamic relation was derived using first and second law of thermodynamics, right? Earlier it was afterwards Clausius obtained the same relation using the Maxwell thermodynamic relation. Okay, the one part, it was derived by Clapeyron by the second law of thermodynamics, whereas Clausius has derived this equation by the use of Maxwell thermodynamic relation. So combining these two efforts, the general term was known as Clausius Clapeyron equation and first latent heat equation. Okay, so let us start the derivation of this equation. We already know from the second thermodynamic relation, that is given as del S upon del V at constant temperature, that is equals to del P upon del T at constant volume. Now if we multiply both sides by T, it will become T into del S upon del V at constant temperature equals to T into del P upon del T at constant volume. If you look at this, T into del S, it will become del Q from the second law of thermodynamics. So it will become del Q upon del V at constant temperature equals to T into del P upon del T at constant volume, right? So the quantity, this del Q upon del V at constant temperature, that represents the amount of heat that is absorbed or released by a unit change of volume at constant temperature T. We can represent this from the expression. This is quite normal. This is del Q upon del V at unit change, that we can replace by 1. So the heat will be at unit change in the volume at constant temperature. This is the amount of heat absorbed or emitted. If our system absorbs or releases the heat that is equivalent to its latent heat L. So if we consider del Q is equals to latent heat equals to L at particular temperature T, and the volume during the change is V1 to V2 for unit mass of gas, then we can write del Q upon del V at constant temperature equals to L upon V2 minus V1. L is the latent heat at that particular temperature, and volume is changing from V1 to V2. So it will become L upon V2 minus V1. We can rearrange it by using this del Q upon del V at T equals to this relation. We can use this relation here. Final form will be L upon V2 minus V1 equals to T into del P upon del T at constant volume, right? If we rearrange this, we get the relation, generalized relation, del P upon del T equals to L upon T into V2 minus V1. And this expression, which gives the relationship between the pressure and the volume and the temperature, or we can, in more generalized way, we can say that gives the relation between the pressure and the latent heat. That equation is known as Clausius Claypeyron equation. So this is again the application of Maxwell's thermodynamic relation. In our next lecture, we will see some other relations also. For today, it is enough. Now we will see, we will do some exercise. We will solve some question to see what you have learned today from the lecture. We have already seen 2 topics. So the question is, the first question for today's quiz is, which is the right set of extensive variables? The first question is mass, pressure and volume. The second option is entropy, internal energy, temperature. The third option is mass, volume and internal energy. And fourth option is mass, entropy and temperature. So we have seen that extensive variables are those variables which define the state of any system in thermal equilibrium, and it should depend on the mass and size of the system. So what are the parameters? The parameters are mass, volume and internal energy. These all depend on the mass or size of the system. So the right answer here is option C. The next question is, which is the right Maxwell's relation? So we need to remember all the Maxwell relations, and that are, so here options are del T upon del V at constant entropy equals to minus del P upon del S at constant V. Okay, Second option is del T upon del P at constant entropy equals to minus del V upon del S at constant pressure. The third option is del T upon del V at constant entropy, and equals to del P upon del S at constant volume. And the fourth option is del T upon del V at constant entropy equals to del V upon del S at constant pressure. So the right answer, unless until you don't remember the Maxwell relation, it is impossible to answer this question. So you must remember all the four Maxwell relation, and the right answer for here is option A, del T upon del V at constant entropy equals to minus del P upon del S at constant volume. Now the next question is, what are the four thermodynamic potentials? That is U, F, H and G, P, T, V and U, P, V, U and F, or none of above. So first we have seen this is internal energy, Helmholtz energy, enthalpy and Gibbs energy. Here pressure, temperature, volume and internal energy. Here pressure, volume, internal energy and Helmholtz energy. So we have already seen that potentials are four: internal energy, Helmholtz energy, enthalpy and Gibbs energy. So the right answer is A for this question. Again, which is the right relation? This is the relation between thermodynamic potential and their variables. We have derived it today's lecture. So the first topic of today's lecture was about this. You have to remember these also to answer this question. I'm giving the answer right now. The answer is option A. V equals to del H upon del P at constant entropy equals to del G upon del P at constant temperature is the right answer. Now the next question is, Helmholtz free energy function is defined by F equals to U plus Ts, F equals to U minus Ts, F equals to U plus Pv, and F equals to U plus Pv minus Ts. So for that, again, you need to remember thermodynamic potential definitions for each of them: internal energy, Helmholtz energy, Gibbs energy, and enthalpy. So the right answer for here is F equals to U minus Ts. So answer B is the correct answer. Next question is, for isobaric adiabatic process, enthalpy is 0, infinite, constant, or altered according to volume. So we will consider that isobaric means the pressure is constant. That means del P is 0. Adiabatic process, the del Q is 0. That means H will be dH will be 0, because dH gives the relation between dH equals to du and sorry, not du, the dP. One term contains dP and another term contains dQ. So dH will be 0. That means if we integrate this equation, it will give H equals to constant. So the right answer will be option C, constant. Okay, what is the relation between enthalpy and Gibbs free energy? H equals to G plus Ts, H equals to G minus Ts, H equals to G plus Pv, and H equals to G minus Pv. So again, you have to remember all the relations between the thermodynamic potential. Here the right answer is H equals to G plus Ts. Okay, so answer A is the correct answer. The next question is, for isothermal isobaric process, G is constant, change with temperature, 0, or none of the above. So for isothermal, dT is 0, temperature is not changing. Isobaric dP is 0, and for the relationship of G, the Gibbs free function, both term will be 0 on the right hand side. That means dG will be equal to 0, and if integrate this equation, we will get G equals to constant. So the right answer is option A. The G value will be constant during an isothermal isobaric process. Next question is, which is the correct answer out of these? Cp is greater than Cv, Cp is less than Cv, and Cp is equals to Cv, or none of the above. So the right answer is option A. The specific heat at constant pressure is always greater than the specific heat at constant volume. Okay, we have derived this, we have learned this in our previous lecture. Now the next question is, del P upon del T equals to L upon T into V2 minus V1 is known as Gibbs relation, Maxwell relation, specific heat equation, or Clausius Clapeyron relation. So definitely we have derived this equation very recently. Today the last topic was related to this, and it was Clausius Claypeyron relation. So the right answer for this question, of course, option D. Okay, so today we have learned about the first topic, thermodynamic potential and their relationship with the variables, right? U, F, H, G with the variables P, V, S, and T, right? The second topic which we have covered today's lecture, the application of Maxwell's thermodynamic relation. We have started with the Maxwell thermodynamic relation, and we derived the equation for a specific heat, that was Cp minus Cv equals to R, and that is known as famous Mayer's relation, right? Then afterwards, we consider it in a more detailed way for perfect gas first, that would derive the Mayer equation. The second was considered for the real gas consideration, and for real gas again we have got some relationship, and that gives us the specific heat equation for real gases. Afterwards, we have moved to the second application of Maxwell thermodynamic relation, and that was Clausius Clapeyron equation, or it is known as first latent heat. Since it was derived by both the scientists, Clausius and Clapeyron, that's why it was combinedly known as Clausius Clapeyron equation. So we have derived using the Maxwell thermodynamic relation again. I hope all the topic which has been discussed in this lecture are clear to you. There should be no doubt. Even if you have some doubt, you can ask your questions by sending your questions by email, or you can comment on this YouTube video also. I would love to answer your queries and questions. Okay. Thank you for your attention. Thank you for listening. Thank you so much.